start. We are still waiting for the meeting that is meeting, but we will start the session. So my name is Rosa. I work for the future. So a possible new collider here is a linear one, click, and it's experiment, because we want not just producing stuff, but also observing new things. And with me there is Steven.
So yes, my name is Steven. I'm originally Canadian, now working at CERN with a Swiss institution. And I work on the Atlas experiment, which is the experiment which you have been using today, their data. So we are going to take you through the session today. So first we're going to have a brief discussion and introduction like we have started right now. We're going to have 15 minutes where we discuss the measurements. And since we have 5 groups today, that means each group is going to have 3 minutes to explain your measurement to everyone else. We'll then have a combination where we will explain combined results from all of your effort today. And then we're going to have some discussion where you can ask us anything you want, whether this is about the physics, the measurement, life at CERN, the weather in Geneva, whatever you feel like asking, we're happy to answer it.
Whatever you have in mind, any question is valid.
Yeah, and then at the very end we'll finish up with a quiz just for fun, to see what you've learned and to give you some last interesting facts. So I guess it's just time to get started then. And I see that our last group has now joined us, which is fantastic.
Okay, so maybe we should also share with you a map to see where all the ingredients are.
1 second. So we've got quite the big group today. We've got 5 different institutes.
All over the world.
Yes.
We have a large map today.
And this really represents also the type of thing we have in Atlas, because Atlas actually has institutes from all over the world. There's more than 100 institutes from more than 30 countries, covering every single continent except for Antarctica. So this is really a global picture, and what we have today with your 5 institutes is just a mini version of exactly what we deal with on an everyday basis here.
Okay. So if we start from north to south, you can see that the red dot on the north is Warwick in UK.
So Warwick, can you hear us? I see you're waving. Fantastic.
Good.
So Warwick, how was your day today? Did you enjoy it?
Yes.
I think I heard a yes there, though it was a bit quiet.
Maybe they just tired.
That's true. End of a long day.
It was a fun day. Okay, we will talk with you, Kurt.
Yeah.
Let's.
Then our second group, I'm sorry, I'm probably going to pronounce this wrong, but Dragoslav, are you there?
Dragoslav is here. Yes, you're right, Dragoslav.
Okay.
We see you. Do you see us?
Yes, we see you too.
Perfect.
Fantastic. Always like the enthusiasm.
So have you had a fun day?
Yeah, I think it was very fun. It was a very interesting day. I think that students had a lot of fun, but would you like to say something? Someone? We had a lot of fun.
Okay, don't be shy. Later.
They had a lot of fun, I think, Eric. That's a good thing to hear. The next.
So we have another institute at Nišu. Nišu, hello.
Hello. It has been a wonderful day. We have done some researching and we have enjoyed it. So we would like to hear about the others. What have they done?
So you're talking a bit too close to the microphone. We can hear you, but we can't understand the words.
I'm sorry. We had a wonderful day and we have done some researching, some learning. It was fun and enjoyable. And we would like to hear about the others, how they spend their day.
Very nice. Okay. As well, we will come to you later. And let's go south to Brazil.
Yes, all the way down to Natal. So Natal, can you hear us?
Natal.
Okay, you're waiting.
Okay, we see you waving, though I think you might have been speaking, but you were very quiet. So I guess it's the opposite problem of Niche. If you don't mind talking a bit closer to the microphone. What time is it there in Natal?
Midday. Wow.
Okay, very good. So not too early then, but I guess you probably had to do some of this in previous days already, or?
Okay. Can you hear us?
We can, you're just very quiet, but we'll increase the volume here whenever you're speaking.
Because of the time difference, we must start 1 day earlier. Otherwise,
Okay.
in the moment.
Okay, well, we're glad you were able to do that, that you were managed to join us here, so thank you for taking that effort.
And not the last institute, the after one for today, Rio de Janeiro. Hello.
Hi, Rio.
There you are.
Fantastic. So, Rio, have you ever done something like this before? Have you worked with anything related to particle physics in the past? We have some previous experts.
Here.
Fantastic. Well, you're going to have to tell us all about it then. We look forward to hearing about it. Okay. So I guess we should probably move on just to get to the actual description of the measurements, but we now know that all of you can hear us and we can hear you, which is a good thing. So let's go back all the way up to our friends in Warwick. So we will switch to showing your results, Warwick, and you have 3 minutes to briefly explain what you have seen.
Do we have a volunteer? Another between the students?
So if you're talking, we're having a hard time understanding. Just for reference, for all the who are not talking, please make sure to mute so that we don't have interruptions in the communication. So just Warwick for now, please be unmuted. Others mute, and Warwick, if you don't mind trying again, we'll hopefully hear you better now. Can you hear us? Yes.
Yes. Perfect.
Hold on a bit.
So Warwick, we're having a hard time hearing you again. I'm not sure if you're talking right now or not, but if so, we can't hear you.
You can hear me?
Yes. Just speak up a little bit more if possible, but otherwise we can raise our volume.
I'll speak a bit more. Yeah, right. We tested 179 events total, and we got 62 events with dead light, PE, with the dead light. And we got 70 events with the dead light with 2 lasers. With 2 new ones. And then we got 19 events with Higgs light with 4 electrons. And finally we got 38 Higgs light events with 2 photons.
Okay.
Very good. It seems you don't have too much data in some of the channels, but I know that there are some other groups today which we've looked ahead in advance where they've had more data there. So it'll be very interesting to see the combination at the end, because really every little piece of data from each little group helps quite a bit. So we'll see more, but thank you for your explanation of what you've seen.
Okay. So we can move to the next group. That is Dragoslav.
Switch this here.
Yes, Dragoslav here. Can you hear us?
Yes, we can hear you very well.
So firstly, we had some technical problems, so our data set is a bit reduced. But with what we had, we plotted the graph, and we would like to focus on the graph with dilepton, with the decay of the set boson on 2 leptons. We have a peak that is formed around 90 GeVs, and we have J psi on 3 and Y on 10.
Very nice.
That's it.
Yeah, very nice. Despite the initial problem, it seems very nice results.
Yeah, I'm glad you were able to at least look at this first channel. Definitely exactly as you say, you have identified the Z boson peak at about 90 GeV, the J side at 3 GeV, and at about 9 or 10 GeV. Technically we call it the upsilon, but it looks very much like a Y. But either way, yes, very much. Very, very well done. You've identified them perfectly. So then we will move to our next group. Thank you.
Thank you.
Hello again. Am I not too loud now?
So Nišu, move the microphone a bit further from your mouth again, please.
Okay, hello. Today has been an interesting day. We have done a lot of stuff. In the beginning we had a lecture about some stuff that we already knew and some stuff new. And also we had a visual tour to CERN and its facilities. And it was somewhat fun to see it because rarely you, if you ever get a chance to see something like that, it's a very special occasion. Also, later we have done in our computing room some comparing of the individual masses of 2 leptons, 4 leptons, photons too, of course. And our results are this. So we have one big peak around 100 GeV, and that's Z boson. Except that we have 2 little peaks that are from also known particles, and the third one and the last one from the 2 leptons is unknown, and we don't have enough data to conclusively say it's some part or some particle or not. In the second in 4 leptons, we don't have much peaks and much diversity as we have in the first one. So we cannot conclusively say about any particles that we had seen in this chart. And in the third chart is similar to the second one, but we have not found, comparing the individual masses of 2 photons, some particular particle.
Okay, thank you. Very complete. You've definitely done a lot here.
Yes.
Yeah, I guess you don't have too much statistics in the middle plot, but again, the combination will help here, and hopefully we'll see something.
Yes,
but a very good, complete explanation. Thank you very much, Nišu.
Thank you. Goodbye.
So south to Natala. Natala, do we have a volunteer to explain your results?
So 1 second, Natala, we have to turn up the volume again here. So please try talking now. Please move the microphone closer to your mouth. We heard the first person, but not the second.
We saw very low energy particles and some kind of very high density particles that we thought that it was simulated. It had too high energy.
That's correct.
I'm not sure, did you want to say anything about the other 2 plots or no? So you've explained the top plot, thank you, but did you want to talk about the middle or the bottom ones, or no? You don't have to. If you
that
Yeah.
was about 120 yeah, and a peak about the puzzle by the 115 G.
Okay. Thank you very much.
Okay.
It's probably a Higgs boson.
Okay.
We will see.
We will definitely see once we have all the combinations. Thank you very much, though, Natal. Definitely, exactly as you said, you were very right to say that in the dileptons, the top plot, the peaks that you see at about 1,000 GeV or 1,500 GeV, these are, as you said, simulated signals. So this is,
Unfortunately, I
yeah,
haven't seen them.
we would love to see those, but so far all we can say is this is what new physics might look like.
Yeah.
So thank you. We will move on then to our final group. So Rio, are you ready?
So we have seen that has welcome back.
Yes. And yes, we heard you, Rio. So please go ahead.
Okay, I'll start the presentation. First plot, you can see a peak at the 3 GeV mark. The mean is 3.07, which is very close to 3. We think that is a J-type particle that decays into 2 leptons. You can see another peak at the 10 mark, more or less. The mean is 9.29, which is close to 9, which is the mass of the Upsilon particle. We think it was an Upsilon particle that decays into 2 leptons. And another peak at the 90 GeV mark. The mean is 89.96, so damn close to 9, which is the mass of the Z particle. We believe that is what happened there. The Z0 decayed into two leptons, and my partner.
Wow. In the first mass peak of the shape psi, we can see muons of mean 3.04 GeV. In the epsilon, we can see 90 with muons with mean 9.60. And in the Z, we can see muons with mean 90.83 GeV. You can see we found more muons than electrons in the Z particle because it's easier to identify the tracks of muons than the electrons, the tracks electrons. Okay.
The second plot is 4 lepton variation mass with a mass peak in 112.5 G. We believe this is rigged.
The third plot is the photon invariant mass, and we couldn't find any peak. It's not what we were expecting. We were hoping to find a peak at 125, but I think we got this histogram because we found some electrons and we thought it was photons.
Okay, very good.
Complete explanation.
Yes, it's impressive how much data you have here. Obviously, your group worked very hard, so good job to all of you.
And you have a lot of people working in this.
So yes, very good explanation of all the different things that you see. And now I think we will actually move on to the combination, at which point we'll explain each one more fully because we'll have the data of not only your institute, but also all of the institutes combined.
Because all the data together will give us a more complete picture, and especially the gamma will give us and people are expecting to see already things. Let's see what happens after the combination.
All right, so let's go into the combination. Just very quickly, you can see how things look with all the data, but let's now look at one at a time. So we'll start with the dielectron distribution. Just a logarithm so you can see it.
Voila.
So this is exactly as all of you have already seen, just now we have more stats so things become, or more statistics, more events so things become even more clear. Just to reiterate for those who were not as aware, there is the J psi particle at 3 GeV, the upsilon particle at about 9 or 10 GeV, the Z particle, or the Z boson at 90 GeV, and then we have two fake signals here at the end. At 1000 GeV, there is what we call a Z prime particle, which is just like the Z at 90, except it's a high mass. And then there's also a more exotic particle at 1500 GeV, which is the graviton, which would have lots of implications if we saw something like that.
Yeah.
But unfortunately, as I've said, this was just simulation. We didn't see this so far, but we're still looking.
And as one of the group has already pointed out, we should use more of nuance in this channel because it is easier from the experimental point of view to identify. So with electrons is a bit harder, so statistically you can see a bit less, but in natural view it's better in toleration.
Yeah, so the number of muons or electrons you identify is really exactly that. It's how many you identify. It's not how many are created. The number of electrons and muons that are created are statistically equivalent. They're approximately equal, but the number that you see can vary depending on how precise you are.
Shall we move to the next one?
Yes.
So for electrons, that is start to be a bit harder with the statistics, and it is correct. For us, it was harder to observe. We have less process to go in this final state with for electrons.
So for here, it's interesting because as you've seen, there is something maybe at about 125. And this is actually, this is my 6th master class this year. This is the first time I've seen that there might be enough data to start to see this. It's hard to say exactly how much of this is expected or how much of this is what we call fakes. It's not directly clear, but just to give you an idea, maybe we'll overlay the amount of data we actually had when we were doing this at the LHC. So if we just look at the 2 inverse femtobarns, you see these 2 little red dots.
That's awesome.
That's all the Higgs events that you would expect in 2 inverse femtobarns. So this was before we claimed any discovery. So as expected, you don't see anything. If we look at 10 inverse femtobarns, so this is now, if you add this to the background distribution that you have, maybe this would stand out enough to see it.
Yeah.
And indeed, it looks like maybe you have seen enough events
I think that we will start to see the observation.
Yeah. So 10 inverse femtobarns is what we had when we made the first observation of a Higgs-like particle. And then there's the 25. And 25 is what we had at the end of run 1 when we started to confirm that not only is this a Higgs-like particle, but this was the Higgs boson.
Yeah.
And so you can see very clearly how much this stands out.
Yeah. Maybe a comment on this is that it's true that here we have very few data, very few Higgs, but it's also true that we have a few of other processes that can mimic this one. We can take as mistake. So this was actually one of our golden channels to see the Higgs. So very few statistics, but very good data.
Exactly. So yeah, if I go back to the 10 inverse femtobarns, which is what we discovered the Higgs with, you'll see that there's only about maybe 8, 9 events here,
10-ish.
maybe 10.
Yeah.
And that was enough to say that we have observed it, just because if you look at all the other events here, you see there's 0 in most of these bins. So really, it stands out. Only 10 events on top of something where you expect 0 or 1 or 2 is enough to confirm it. And then let's go to the funnest one, the final one.
The hardest one.
The hardest, yes. The diphoton.
The diphoton.
Yes.
So was as well another of our golden channel, but here things we knew that we need more than 10 events.
So you don't, as the Rio de Janeiro group pointed out, unfortunately you do not see anything at 125 GeV here with the Higgs. This was completely expected. So if we look at the amount of data, again, 2 inverse femtobarns is before we could see anything. And this, you see the little pink or red on top of the green. There's not much.
No.
If you go to then 10 inverse femtobarns, which is where we observed the Higgs for the first time, you'll start to see it, but it's still not too obvious.
We have powerful tool because to estimate that over this shape of the background, there could have been something, statistics is a really good job for us.
Yes. And then finally with 25, you'll notice that the size of the red area didn't grow, but the change from one green bar to the next green bar has gotten smaller. And that change is actually how you have seen the resonance, which is the Higgs. Because we have this large background, we've got 3,500 events here of green, and then only maybe like 20 or 30 events in red. But because we have this distribution which is so smooth, and there's one area which is not smooth on that, you can identify it.
You can see little bit just sticking out of the.
So we actually have an animation which shows as we recorded data. So this is now being shown.
So look at the vertical axis that is growing and growing, and the peak as well is growing and growing.
Yep. And ultimately, this was the observation. The blue line was that background, and that red line over top of it is the very, very small deviation, which tells you you have seen a new particle.
Yeah, and this is why, thanks to our very precise detector that can go to very precision, so you see that there is error bars in response. If you collect enough statistics, at a certain point, the error bars become smaller and smaller, so that little data became significant.
Exactly. So one other very interesting thing to talk about here is not only the combination of data from all of your different results, but also the combination between different ways of looking at the data. So we have on the top the dilepton, the middle the four-lepton, and the bottom the diphoton. And it's only by looking at these different channels that we could say whether this was a Higgs boson or not. Because, as you said, if you see something at 125 GeV, this might be a Higgs boson, but we can't confirm. In fact, seeing it in this diphoton or two-photon channel was very important for us to understand this was Higgs. Because we have never had a particle before the Higgs which can decay to two photons just because of some quantum mechanics properties of these particles. But the Higgs can decay to two photons. So seeing something that decays to two photons was our first hint that this could be the Higgs. But maybe we have something else that decays to two photons. And it's only when we also see that it can decay to four leptons that we then can confirm this is the Higgs. Exactly, and then more and more and more. So really, at CERN, everything we do is combinations. We have combinations of data as we get more data. We have combinations between different ways of looking at the data. And then we have combinations between the effort of different institutes within an experiment. And then we have the combination between ATLAS and CMS. So combinations are a fundamental part of what we do here at CERN, and working together, and there's so many different things that go into this, that it's really a hugely multinational project, to the extent to which we have 3,000 people, 3,000 physicists in ATLAS working to get these results.
So I think that it can be enough for the combination. Yes. We hope that we have convinced you that it was an important process. And I think that it's time for questions.
Yes, so let us then move back to asking the different groups. At this point in time, you are welcome to ask us anything. This can be about the combination, again, about life at CERN, whatever you feel like. Sci-fi, yeah, we've had some sci-fi questions too. We can't promise to answer all sci-fi questions, but we'll do our best. So we'll start with our friends in Warwick. Do you have any questions you would like to ask us?
We'll start with the one question for the group and maybe
yeah, so just one question for now. That's a good point. Thank you, Rosa. Just due to the lack of time and the number of groups, we'll start with one question, and then if there's sufficient time, we'll go around one more time.
Yeah, hi. Explain what spin is.
Spin. Wow, that's... You're going right for the hard questions, aren't you, Warwick? Good job. Okay, so what we were just talking about here, and the reason that we wanted to have this diphoton channel is because of this spin. So spin is a quantum mechanical property which we can describe it mathematically, and if you talk about we can identify whether something has a positive or a negative spin, but we don't have a thorough explanation in the sense that you can understand outside of quantum mechanics and without seeing an experiment.
Often it's identified as the rotation of the particle, because it's true, the spin is a rotation matrix, but it's a rotation matrix in a different space, in a mathematical space. So, but usually for making them understand when you still don't have the matrix, you can imagine like the particle to spinning around an axis.
At a given rate,
but this is not, just keep the idea and forget about what I've said.
So the general example here is that bosons have an integer spin, so spin 0, 1, or 2, and what we call fermions, so this is electrons, positrons, quarks, whatever, have a spin of plus or minus 1/2. So the Higgs is special because it's the first spin 0 particle we have, and the reason, that's why we wanted to see this diphoton. All the other bosons we've seen before now are spin 1. So if you take plus 1 and minus 1, you can make spin 0, which is why you can have something which the Higgs particle decay to 2 photons, but we've never had anything like that before now. So I understand this is probably not the most satisfactory explanation for you. For that, you would need to take some more quantum mechanics to get to the mathematical representation.
At university?
Yes.
To take a quantum mechanics course at university?
But the way you could think about it is spin is a mathematical explanation for a property of the particles that we have seen in the lab.
And there are some rules that conservation of all, like energy conservation, we have some rules concerning spin as well.
So yes, extremely hard question. Hopefully you understand it a little bit better now, and now I think we have to move on to the next group. So let's go then to, who is next?
Dragoslav.
Oh yes, Dragoslav, you're next. Do you have any question you'd like to ask us? Hopefully a bit easier.
I have one question. How many attempts or events you have to process to be sure that you found a new particle, in this case Higgs boson?
That's a good question.
That's a very good question. So it depends again on the events. So we have seen the case of the Higgs that for the 4 lepton final state, just 10 events were enough. But for the gamma, I think that were more than 100, around 200, something like that.
Possibly even more than that.
Even more. And so it depends on the quantity of other events that will end up in the same region. So in the various parts, in the diphoton, you have a lot of other events. These things that we call background, that was in green. So it is a combination of the two.
But then beyond that, there's also the factor, I think you're also asking about how many other events are there, because there's these processes, the number of events to identify something are very rare. So you have to have a ridiculous number of collisions at the LHC to have 10 events that decay to 4 leptons or things like that. So we had billions and billions of events.
But LHC is
I'm sorry, we couldn't hear you. Can you repeat that?
In which point in research can you say that you are sure that you've discovered a new particle? That it's final, that you cannot...
Yeah, so... No, we heard you. That's a question.
The results conclude that you are sure that you find some new particle.
Yeah, it's a good question, and it's also very challenging to answer that definitively. We always work in statistics, and this means that we are talking about probabilities. So what we do is we wait till we have something called 5 sigma, which basically means that the probability of this being a statistical fluctuation is 1 in, I don't know, 10 million or 100 million, something like that. And then we also require that you see it in both ATLAS and CMS. So seeing it in 2 different experiments rules out the possibility of a detected effect. And then seeing it less than like 1 in 10 million in each experiment says that this is not just statistics. This is the general guideline for claiming a discovery, but after that you of course continue to improve this in future years. So we'll move on now to the next Nish. Thank you for the question, and Nish, you have one for us.
Greetings from Niš, Serbia. I have a question.
Nish? The problem, microphone further away, please.
Can you hear me now?
A little bit further, please.
Now?
Okay.
In recent years, in pop culture, there has been much talk about the multiverse theory. Can this be proven? And if it can't, is it worth discussing at all?
I'm sorry, you're going to have to try again with a bit further away. It's still coming through gargled. I'm very sorry about
that. In recent years, in pop culture, there has been much talk about the multiverse theory. Can this be proven? And if it can't, is it worth talking about?
Okay. Yeah, so multiverse. Okay. I think there's 2 sides of what you're asking. There's multiverse is one possible interpretation of quantum mechanics. We cannot prove nor disprove it in the standard sense because when you talk about a multiverse, if you say every decision I make causes a split such that there's one universe which goes in one way and one universe that goes in another way. And we cannot, without seeing these universes, definitively prove whether this is true or false. What we can do is look at alternative dimensions, which is not the same as multiverse, but I'll come to that in a second. So if we talk about watching for new particles which can go into dimensions that we can't view, then this provides evidence for something along the lines of string theory, such that if we have a graviton, this is strong evidence that string theory might be real, and string theory then demands the existence of types of things such as multiverse theory. So we don't have a direct way of proving whether multiverse exists or not, but if we find a graviton at the LHC, this would be indirect evidence that would suggest it's true. I hope that answers your question.
Thanks a lot. We have actually one more question. Hello. The other question that we have is not so related to physics in that manner. The question is, what kind of personal traits are needed to work as a physicist in CERN?
I'm sorry, can you repeat that? We heard the first half of what you said and not the second half.
Okay, I have to ask you, what kind of personal traits do you need to work at CERN? And what kind of relations
working at CERN.
Working at CERN.
So this is a question, thank you for bringing it up. If you didn't bring it up, we were going to answer it anyway. So coming to CERN, there's lots of different ways, and I would strongly encourage it. It's an amazing opportunity. If you like science, whether it's physics, we also have biology, radiation therapy, computing. There's lots of different things here. There's lots of ways to come to CERN.
Yeah, I would say that there is
for anyone in science, there are, at high school level, there are 1 or 2 week placements where you can just come to get the feeling of CERN. It's not many positions, but you are welcome to apply for them, and hopefully you can come. At undergraduate level, so once you're in your, taking your degree studies in physics or computer science or accelerator physics, there's a few different areas. We have what's called CERN summer students. So both of us actually will have a summer student this year. And there's 700 or 800 summer students each year who will then come to CERN for usually 2 months, where they will go through courses and also do some research at CERN. And you are funded to do this. Yes. You'll have a supervisor who is a postdoc like one of us, but you will be doing both research at CERN. And then if you decide to continue on into graduate school, so you're doing graduate work in particle physics in particular, you will come to CERN. It's not a question. As I said, I was from Canada. I did my graduate work in Canada, and Canada's far away. But they still guarantee 1 year at CERN, because in particle physics, CERN is the center of particle physics, and if you're doing this, then you will come to CERN for part of your time. It's pretty much a guarantee. At the very least, you will come to visit. So as you go farther and farther in, you will end up finding that you'll have more and more opportunities to come to CERN. So, very good question. Thank you very much. Now we will have to move on to our friends in Natal.
Natal? Any questions?
And we will up our volume. Yes, we hear you.
My question is about the capacity.
I'm sorry, can people who are not Natal please mute right now? We're getting a bit of feedback here. Please try again, Natal.
I believe this helps get better results and find but what do you think the maximum capacity capacity of the
Okay, I had a hard time to hear you. You said there's been a new discovery, or but talking about reaching a limit. Can you just specify maybe? Okay, I'm going to mute everyone but Natal right now. I'll unmute you later. Give me 1 second.
Yeah.
The accelerator can produce like 10 tabs or something like 14 tabs. I don't know exactly what it is, but what do you think?
We will see if at the end we try to push a bit. This is very common that at the end you try of the life of the machine, you try to get out everything that you can from the current machine. When you shut it down, then there is a long period to build a new one. And I'm working for one of the proposals of the future, and it's a linear, and we can go up to 3 dB. But the energy is going to be all used in the collision. It's a bit different.
An important point, because when you talk about a normal collider, a collider like we have at the LHC, when you collide protons, as Rosa said, we can go to 14 TeV, but most of that energy is not colliding. Most of that energy, because a proton has quarks and gluons in it, most of that energy is just going down the beam pipe. Only part of it collides.
So usually, it's okay, if you're lucky you can get the collision up to using 14 TeV, but usually the LHC was able to explore the 1 TeV scale.
Yeah.
So click instead is going up to the 3 TeV. And otherwise we have proposal of other circular collider that needs to be larger radius, so they are talking about 100 kilometers, while the LHC is just 27 kilometers. And with here, with this collider, maybe also here CERN, we can reach energy up to 100 TeV. Otherwise, there is something a bit smaller, proposed for China, where the energy is going to be around 70 TeV. So yes, we are planning to go higher. And what you believe it for this is the technological limit. But there are interesting developments like plasma field accelerator that maybe will open a revolution in our field.
So in general, the limit is how big your ring is and how strong your magnets are, because you need to bend particles that are going faster and faster in a ring. So as you increase the strength of your magnets with better technology, you can go to higher energies. And as you build a larger ring, so 100 kilometers instead of 27 kilometers, you can go to higher energies. But we also, as Rosa was saying, we have things, alternate technologies which might completely change this.
Yeah.
So it takes 20 to 30 years, though, to build a new experiment. So
that's why we are
it's going to take a long time.
So yes, we are the simulation that we will build and work on the future, so it's very important. So let's go to Rio for our last question.
Okay. You can show the plots again, please.
This one's.
Okay, yes.
Okay, thank you. We have a high peak in 103, something about 103. I would like to know which particle it is.
The photon invariant mass.
The photon invariant mass.
The photon invariant.
So the diphoton invariant mass, what you are seeing here, I mean, it looks like peaks, but nothing here is what we actually call statistically significant. So if we had another equal amount of data, you would see that these peaks would be in different locations, so when you add them together, they would average out or something like that. So ultimately, nothing you see here is a peak representing a new particle. All it is a statement that we need more data to understand this distribution better.
So this is what we call a fluctuation. So of course, when you take a measurement, you're going to get always the same outcome. This is how quantum physics work. So you need to take a lot of measurements and combine them and keep taking them and see the evolution with time. So what Steven showed you before, it was very nice plot by Afras, and where you can see the evolution by time, and you see consistent. So see, at the start, they just put data. So there are kind of peaks around the curve, and then they stabilize, and there is just one that is survived. So it's what is exactly this that is happening in your plot.
Yep. And ultimately, if you had, so what you have done is you have identified events today. You have not assigned what we call uncertainties to those events. If we had assigned uncertainties here, you would have seen that all of these peaks would be within the uncertainty bands and that there's nothing sticking out of that just because, that's the way it is. You need more data and you need a better understanding of your detector to really see the small things. So I hope that answers your question.
Okay, thank you.
Okay. So we
are actually pretty much exactly on time, so unfortunately we don't have time for another round of questions, but we will move to the quiz at this time.
So everyone has the answer sheet, because we are going to start the quiz.
So can people wave if you have the answer sheet?
I don't see that. I'm waiting, I'm a bit worried.
Yeah, see at least one group.
Okay, one group has the answer sheet, the other one.
Okay.
Okay, we will be confident that you will be given with the answer sheet. Otherwise, they are not mandatory.
Yes.
Just think to the answer.
Yeah, this is just for fun, so let's go. There will be 7 questions. That's the time you're doing right now.
What's our name?
Rio, we are going to mute you right now because you are not muted. You can unmute later if needed. If I can. Okay. So Rio, we've muted you temporarily right now. We'll unmute you later.
Okay.
Okay, so going on, so there's the rules of the game. There's 7 questions, and there's 4 answers to choose from, A, B, C, and D. Make sure to mark your answer on your sheet, or if you don't have a sheet, just make sure you know what your answer was before the time ends. We will then reveal the correct answer, and if you've answered correctly, you can take it off and go to the next energy level.
It is more difficult and difficult. It's increasing,
Yes. The last level is pretty hard, so I hope you're ready for it.
70 is not for everyone.
Yeah. So let's see what energy level you can reach. And please note, this really is a quiz for fun, not for competition. We're not going to compare results. So just enjoy yourself, and we hope that you're going to learn a couple of interesting new facts here.
Okay, so let's start. Ready, set, go! So, first question. Which particle is the mediator of the strong force? A, neutralino. B, male. C, gluon. D.
And your time starts now. Okay, your time is up. And the answer is C, the gluon. So you've probably covered this in your discussions earlier. If not, then yes, the answer is the gluon is the mediator of the strong force. This is what holds our atoms together. The second question, what percentage of all the matter and energy in our universe do we know almost nothing about?
Nothing.
Yes, absolutely nothing. Well, almost nothing. We don't exist. Is it A, 13%, B, 96%, C, 100%, or D, 32.8%? And your time starts now. Okay, your time is up.
And the answer is D, 96%. So from astrophysical measurement, we know that the ordinary matter that we study in the and so on is just 4% of the ordinary. Then we have 24% that is matter, and that is something that we don't know much about. And then we have the rest that is still even more unknown, and it is the dark energy. And
there's lots of theories for what this is, but at this point in time, we don't have anything that actually confirms or explains
a
it.
lot of things to work on.
Yes. Okay, the third question.
Okay. Which of the following is an experiment at the LHC? A, B, A, C, Ohio, D, Flappy.
Okay, your time starts now.
Alice?
And your time is up. And the answer was A, Alice. So we have 4 detectors at the LHC. We have 2 what we call general purpose detectors, which means they do everything, which are Atlas and CMS. And then we have 2 precision detectors for special cases, which is LHCb, which runs mostly in proton-proton. And then this one, Alice, which is actually very special, because rather than colliding protons at the LHC, for Alice, we actually collide lead ions, where lead is a very, very big particle compared to the proton, which means that it's a very different environment that they're working in.
There is very huge splashes. If you look at the main display, they are beautiful.
Yeah, there's stuff everywhere. So yes, Alice was the answer. So the fourth question. It's me. Okay, so which 2 people won the Nobel Prize for Physics in 2013? Is it A, Stephen Hawking and Marie Curie, B, Peter Higgs and Stephen Hawking, C, François Englert and Albert Einstein, or D, Peter Higgs and François Englert? And your time starts now. Okay, your time is up.
And he passed away before 2013. And there are other scientists that consider the form the gang of 6 that was also very close
Yeah, so there were 6 people who discovered this in the span of 2 or 3 months, I think it was.
Yeah, and they were expanding the field around, but Peter Higgs was making the point that this Higgs should have mass. So for us, it wouldn't be a discriminated thing because we could observe it.
Yes.
So that was the breakthrough.
Okay, question 5.
Which of the following technological innovation was invented at CERN? A. The teleporter. B. The World Wide Web. C. 4G mobile phones. D. Sharp later on the right.
The 4G mobile networks. Sharks with lasers on their heads.
Okay, your time is up. And the answer was B, the World Wide Web. So one of the things we do at CERN is work with enormous amounts of data. Data so large that we can't record everything. We have to select what we record. And then after that, we can't process it with a giant grid computing cluster that we have at CERN. So we have to send it to grid computing clusters around the world. So this was originally for the World Wide Web. We needed to be able to share data. And it has since evolved, and I think everyone now, well, we're talking using the World Wide Web right now, so it's very useful. There's a lot of things that have been produced as a result of what we need and that have now become used around the world.
It's a really boost for technological innovation. What we are asking for our experiment for processing data is so at the frontier of what is the truth, but it really make it happen, and then you can find application and so.
Okay, so we'll move on to the second last question. During a long run, where the proton beams might circulate for up to 10 hours, how far will these protons have traveled if they have not interacted? Is it A, the distance from CERN to the Sun and back? B, the distance from CERN to the center of Geneva? C, the distance from CERN to Neptune and back? Or D, the distance around the circumference of the Earth? And your time starts now.
Starts getting harder. Maybe just a hint. A call that the proton goes very close to the speed of light, so very fast.
So your time is up. The answer?
And the answer is C, the distance from CERN and to Neptune and back.
So if you want to actually quantify how fast those protons are going, it's 0.9999999 the speed of light. It's fast. Okay.
Okay, this brings us to the final question. So, this is very hard, but which elementary particle is most common in your body? A, the up quark, B, the down quark, C, electron, D, the bottom quark.
Your time starts now. Okay, your time is up. And the answer was A, the up quark. So this one is a very hard one, and the way you have to think about it is that the most common particle in your body is actually the hydrogen atom. And the hydrogen atom consists of a proton and an electron. But the proton has 2 up quarks, 1 down quark, and then there's the electron, which means you have 2 up quarks, making it the most common particle in your body.
Okay.
So, we hope that you had a good time. I don't know how many of you managed to make it all the way to the end. If you did, congratulations. I don't know if I did the first time, so good job. Either way, we hope that you enjoyed it. There's a lot of fun things going on here at CERN.
We really hope to see your please continue in physics. Try to come here, as only to visit.
Yep.
We really hope to see you again. And this will be a very long day for you. So.
Thank you very much, everyone. It was wonderful to meet you. We hope you had a good time, and maybe we'll see you in person.
Idemo sa Par komentara, znači ovdje ne ako se to je